Hello, everyone, and thank you for joining us for today's session. My name is Danny, and I'm the event planner for the New York Reactor space. Before we start, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional, and on topic. Useful links will be shared in the chat. The session is recorded and will be available on demand 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. It'll run for approximately 1 hour with time for questions throughout. I will now turn it over to our speaker for introductions.
Hello all, and welcome to this Microsoft Reactor series focusing on GitHub Advanced Security. My name is Adam Borelowitz, and I'm an application security executive here at GitHub. I'm joined by my co-presenter, who will ask to introduce himself now.
Howdy, I'm Charlie Rice. I'm a field security specialist here at GitHub.
Today, we are excited to walk you through GitHub Advanced Security and improving application security in the age of AI with GitHub Advanced Security. To start, we are going to set the stage with just a few stats on the state of application security today and the current path of remediation that most developers take. 94% of applications have flaws and vulnerabilities, and half of those are greater than a year old, which we define as security debt. 89.4% of security debt is existing in first-party code. And the impact that security debt has on organizations impacts both your ability to deliver business value, because it slows down your time to deliver software to production and to your customers, and it impacts the ability for developers to actually remediate vulnerabilities at scale, as the amount of vulnerabilities significantly outnumbers the amount of time they have to focus on that remediation. Now, how does mounting security debt impact organizations? It increases the probability of a security breach, which can result in reputational damage, fines from the government, lost customer confidence, and associated costs with that. It also results in disruptions to developer flows. Integrating fixes into legacy systems involves a steep learning curve and extensive time to get up to speed, taking developers away from priority work. It also results in downstream complexity. Existing vulnerabilities in dependent code that is called in other applications can result in build-breaking flaws, and most developers are not experts in security, nor can we expect them to be. So coming up with systems to empower them to become make it easier for them to deliver vulnerability fixes at scale is an improvement for their day-to-day life. And it also increases friction between security and dev. Both teams need to be in sync to understand the problem and develop a program to go and remediate the issues. With nuanced and sometimes conflicting priorities, ease of use, and developer workflow, or where GAS has a strong differentiation in the market. Now, GitHub Advanced Security at a high level has built 3 core types of application security every single company should be doing right in the enterprise platform. Starting in the top right here, software composition analysis is included with your GitHub Enterprise license, but I think it's important to highlight where it sits within the context of the Advanced Security Suite to showcase all the AppSec capabilities we offer. SCA looks for known vulnerabilities in code that show up commonly in your manifest files, as well as vulnerable transitive dependencies. We also identify the associated license obligations. Now, exclusive to the Advanced Security Suite is static application security testing, which identifies vulnerabilities accidentally introduced in the code that your developers have written. Vulnerabilities like the OWASP top 10, injection type issues, and SAN CWE top 25 weaknesses. Next is secret scanning, which identifies leaked keys or tokens at scale across all of your GitHub repositories or anywhere a person can put text into GitHub. Now, what's great about these automated security capabilities is they're built into the platform, which helps simplify implementation considerably. The last two are functionality that really differentiate GitHub as an AppSec platform. First is the ability for our customers to integrate any third-party AppSec capability into GitHub as long as they export a SAR file, which the most relevant AppSec tools will do. From there, we will aggregate alerts from our built-in capabilities and any third-party tools you've integrated, and we produce them for dev teams at the project level for security teams and engineering leadership at the org and enterprise account levels as well. This way, you have flexibility to leverage any of our capabilities or third-party ones, and your teams see consistent views within GitHub. We also have tons of great SIM integrations to elevate critical findings to your security operations teams. Now, from what we've seen so far, I think it's pretty clear from any experience you have leveraging AppSec tools, the industry does not have a detection problem. It has a remediation problem. With the majority of alerts existing in applications for more than a year, the goal here is not just to know that those vulnerabilities exist, but to remediate them at scale and to ensure the developers are getting the education required to not introduce more vulnerabilities as they are writing new code for your business. Now, there are three persistent challenges that always come up when we talk about remediation. First, as many companies started to shift left, false positives quickly overwhelm developers and cause them to lose trust in security alerts. How can you shift left if folks won't look at the findings? Second, context switching between where the developer works and where the security alerts and remediation guidance lives wastes a lot of developer time. They're oftentimes having results for SCA coming from one tool, static analysis from another, dynamic from a third. And when those results are traditionally brought to them through tickets, they're often not even aware of those vulnerabilities until a ticket shows up. And even then, there's no guarantee that what they've been assigned to work on is something that is truly exploitable inside of their applications. And lastly, for issues that are real true positives, it can be really difficult for developers to make those fixes because they aren't security experts. Now, with the introduction of AI into application security, we're able to turbocharge that journey for developers, educate them at the time of detection, and help them remediate those vulnerabilities without having to be security experts. Last year, we introduced code scanning autofix, which is designed to help developers learn why vulnerabilities exist inside of their code and deliver the fixes for them at the time of detection. We have brought this capability to the PR checks that exist inside of GitHub static analysis capabilities. As the developer is checking in code and submitting a PR, we'll inform them if that code introduces a net new vulnerability. And instead of just telling them, hey, you've introduced a vulnerability, good luck, you can't go to production, we'll inform them at that time why this vulnerability exists, the steps that are required to fix that vulnerability, and finally, we'll generate that fix for them. All that developer has to do is review the fix that's been suggested, commit it back to that pull request. We'll retest it, ensure that that vulnerability has actually been remediated, which allows the developer to get out to production significantly faster and removes the need for security teams to spend a lot of time triaging and working with development teams to fix those vulnerabilities, significantly reducing that friction between those two teams. This supports all of the languages that we have across CodeQL or our static analysis tool support, and it helps prevent the introduction of vulnerabilities, again, without increasing the friction to deliver business value. Now, this brings us to some stats on what we've seen so far from our customers using this since we released it last November. We've seen 3 times faster fixes in pull request, 28 minutes with Copilot autofix versus 1.5 hours manually, 7 times faster fixes for cross-site scripting vulnerabilities, and 12 times faster fixes for SQL injection vulnerabilities. Now, developers are introducing these types of vulnerabilities most often compared to other ones, but it does not mean they're experts in understanding how to fix it. So that time savings is being driven by us generating that fix at the time of detection, allowing them to deliver that business value. We've also brought AA capabilities to secret scanning as well. Traditionally, when developers are looking or tools are looking to detect secrets inside of your code, they're using regex to detect things like AWS keys, Azure keys, Google Cloud keys, which are really easy to detect accurately because there's a defined pattern for them. But when you're looking for other types of data, let's say, for example, passwords, using a regex to detect that type of information traditionally results in incredibly high false positive rates. We are now leveraging Copilot behind the scenes to help detect things like passwords at significantly lower false positive rates, allowing developers to not just ignore findings that are coming from security teams because they can be rest assured that what we detected is more likely than not to be an accurate detection of a password, allowing them to understand how to fix that vulnerability or that exposed piece of data much faster without having to be overwhelmed with significant amounts of tickets. What we'll be announcing next week, and so you're getting a sneak peek today, is the ability to scale the power of auto-fix with security campaigns. A campaign is something we'll be delivering inside of GitHub that allows you to encapsulate some number of vulnerabilities that exist in your backlog and assign that work out to developers. And instead of just saying, here's 50 things you have to go and work on, we'll inform them of those 50 issues, inform them that there's an auto fix available delivered by the Copilot auto fix engine. It'll give the developers that just-in-time education on why this vulnerability exists, show them the fix that has been generated, and allow them to either submit those one by one or submit them in bulk once they've reviewed those issues, really allowing you to mitigate risk at scale significantly faster without relying on a number of Zoom calls, Teams, or Slack messages across your business, so you can continue to drive business value while staying secure at the same time. Now, I'm going to hand it over to my colleague, Charlie, who's going to go through a demo of these capabilities that we've just gone through as part of this deck.
Thanks, Adam. So what we're looking at here are the 4 pillars of GitHub Advanced Security. I'm going to talk to you a little bit about each of these and how we are using AI to improve the efficiency of your developers creating secure software and also securing your existing software. We'll talk about the security overview. That's going to be where we'll get the 40,000-foot view of where things stand with regard to application security across your organization. We can also, from there, dig down into the details, so we can go from that overview, that high-level view, all the way down into individual repositories or even individual findings. We'll talk a little bit about Dependabot. We're going to focus a lot on CodeQL because, as Adam showed you, we've got the autofix available now for that, Copilot autofix, and that's really a game-changing feature for securing your applications. We'll talk about a little bit how CodeQL scans work and then how autofix is going to help take care of those. And then we'll also look at secret scanning, and I'll show you some of the kinds of secrets that we can find with the Copilot-powered secret scanning that Adam was talking about. So here we are in a GitHub repository, and we're looking at the backlog of findings in an intentionally vulnerable application. Now, when we turn on CodeQL for an application, and even more so when we turn it on for a large set of applications, there are always findings, or almost always findings. And when we turn it on again across a large organization, there are usually a lot of findings. And it's not something that where the developers can just drop what they're doing and go focus on these vulnerabilities that have been identified. Your developers still have other priorities. They have features that they have to introduce. They have bugs they need to fix. Typically, a lot of this stuff ends up on the backlog and starts to get prioritized in. So here we are looking at that backlog for this intentionally vulnerable application. Now, as a developer, when I'm going through my day-to-day work, I don't need to see this backlog. What I need to see is the findings that are relevant to the changes that I'm making. So a typical developer workflow is a developer pulls down the code, they create a branch, they make their changes to that branch, and then they submit a pull request to merge those changes into the default development branch. And that's where we like to scan, is at that pull request. Because if we scan there, we can block new findings from ever becoming security debt that has to be dealt with later. So let's look at what that workflow might look like. Here we have a developer who has followed that process I talked about. They pulled down the code, created the branch, introduced their changes, and now submitted a pull request to merge those changes back into the default development branch. So if we scroll down to the bottom, we can see that when the pull request was submitted, all of these scans, all of these checks automatically ran, and we see we have a failure with the code scanning results for CodeQL. If I scroll up, I can see that failure is due to a code injection vulnerability. If I click Show Paths, I can see the data flow where the potentially tainted data is coming into the application here, the source. I can see the step where that potentially tainted data is operated on. And then finally, I see the sink where this potentially tainted data is being used in an insecure way without having ever been sanitized, thus introducing this code injection vulnerability. Now, if I don't know how to fix a code injection vulnerability, or I want to understand it a little bit better, I can hit Show More Details here, expand this, and I'm going to get a description of what is code injection, recommendation on how to avoid code injection, and some sample code telling me, hey, this is a way that we do want to do this, and a way that we don't want to do this. And finally, I'm going to get some references here where I can go learn more than I ever wanted to know about code injection. So we're not just throwing the problems over the wall to the developer and saying, hey, you messed up, go fix it. We're giving them the information they need to understand the problem and to fix the problem. And also, like Adam mentioned, to start understanding better what they need to do to not introduce similar problems in the future. So this is what we've been doing for years with CodeQL. What we've introduced recently is AutoFix powered by Copilot. This does not require a Copilot license. This is a feature of GitHub Advanced Security. And we can see here, Copilot is giving us a natural language description of why we have code injection in this particular instance. So this is not a boilerplate, oh, this is what code injection is. Or this is not what code injection is. This is why you have code injection in this particular instance. And if we scroll a little bit further, we can see here, the Copilot is actually giving us code to fix the problem. If I'm happy with this code, I can commit it to, and it will commit it to my branch that I've already submitted here. I submitted the pull request for. It'll commit that code to my branch, and then it will automatically rerun all the checks to make sure that A, we fixed the problem, and B, we haven't introduced any other problems. It'll also rerun, of course, any unit testing or other automated testing that you have configured for your branch. If I'm not satisfied with that, I can edit it. I can either pull it down and edit it in my local environment, or I can edit it right here in the GitHub user interface. So this is really game-changing for identifying and fixing these sorts of things immediately. Like Adam mentioned, we're seeing much faster fixes to problems like this, and this is really handy for getting moving forward with our pull requests and new code. But where it's also going to be very valuable is in our backlog. Now, I mentioned, when we have these, when we turn things on, when we turn on CodeQL for an organization, for an enterprise, usually there are just tons and tons of findings. And a lot of it goes in the backlog and stays in the backlog because everybody's in a rush to move forward. This is going to be game-changing for fixing that, for trying to burn down that backlog of vulnerabilities. But one of the things we need to be able to do is focus developer attention on it. And for that, we're introducing campaigns. So campaigns are a way for your security teams and for your development management teams to focus developer attention on what needs to be fixed and using those auto fixes to fix them. We're able to generate autofix for about 76% of the findings that we surface with CodeQL. We're really happy with that number, but we're also looking to improve that. We're working to improve that number. So what we're looking at here is a campaign that I've created, and I created this by going to all of the findings to the organization level view of findings for code scanning within my organization. I filtered it down to the things that I wanted to identify, the things that I wanted to work on, which was as we saw there, was SQL injection vulnerabilities across a couple of repositories. I can see now I have all of these findings that are now part of my campaign. I've given the team 37 days to go through and fix these findings. We've got 24 alerts that we're going to try to knock out in that time. And we can see I just started this today. No progress yet, 24 alerts left. If I click into these, we'll see that Copilot has already attempted to, and in most cases has, generated an autofix for them. And I can commit this finding to a new branch or commit this autofix to a new branch. If I choose to do so, it's going to create a new branch, and then it's going to give me the opportunity to make any changes I want to make before I submit the pull request for that branch. And then it will, again, run all of our automated all of our automated testing to make sure that I fixed the problem and not introduced any other problems. I can also, if I go to the repository view for a finding, now I'm looking at all the findings in the campaign, in this particular campaign that are part of this repository. And I can even come through and I can select multiple findings with their auto fixes and commit those to a new branch. And then once I'm satisfied with those, again, submit my PR and have everything, have all the automated checks run again. So this is really going to be game changing when it comes to the ability to burn down that security debt, to help focus developer attention on that security debt, and really making a difference in the security of our legacy applications. So those are the auto-fix aspects of CodeQL. I'm going to talk a little bit also about just how we do a CodeQL scan, or what happens when we do a CodeQL scan. When we do a CodeQL scan, we basically create a database representation of your application. For compiled applications, we actually hook into the compiler and gather information about the application as it's built, and use that as part and contribute that to that database representation of your application. Once we have that database representation of the application, we run CodeQL queries against it. So CodeQL is both the name of the tool and also the name of the open source language that we use to look for patterns or vulnerabilities in the application. All of our CodeQL queries are open source. So if I go into a finding and I come down here and I click View Source, I can actually see the CodeQL that we are using to look for this particular vulnerability. And this is infinitely tunable. I can create my own queries, I can create my own query sets, and I can run those against any of the applications. If I persist the database representations of the code, I can even run ad hoc CodeQL queries against those databases. So it's a very powerful tool enabling you to find patterns in data. That database representation, once we have that and we start running our queries, what we're doing is we're identifying all of the sources where potentially tainted data is coming into the application, all of the sinks where that potentially tainted data is used, and then all of the potential data paths from any source to any sink. And once we've got all of those data flows that are represented within the application, then we start looking along those data flows for vulnerable patterns or for mitigating things and things like that. And that's how we're identifying vulnerabilities in the applications with a CodeQL scan. And all of the CodeQL scans are in this, or all of the CodeQL queries rather, are in the same repository, which, like I said, is open source and available to anybody to review the different queries for the different kinds of types of vulnerabilities across each of the different languages that we cover. Another cool feature of CodeQL is that we give you the ability to within code scanning to view results from other applications that output their results in static analysis results interchange format, or serif format. So any tool that outputs its data in serif format, its findings in serif format, we're able to upload those into the repository, and you'll be able to see those findings here. Actually, let's go ahead and have a look at a broader set. Here in our demo organization, we have, I think, 2,600 roughly active repositories. And across those 2,600 repositories, we've integrated quite a number of different tools that do output their data in serif format. So you can see Gripe, Anchor, Trivy, some various PHP scanners, some IAC scanners, large number of applications that give you the ability to, again, view these right here in the CodeQL code scanning interface. This is really useful for reducing the context switching that your developers need to do. Your developers are already spending their time in GitHub, so this helps them to get things done without having to interrupt their normal workflow. So that is CodeQL and code scanning. Next, I'm going to talk a little bit about secret scanning. So secret scanning, like Adam mentioned, is our solution for identifying secrets that have been checked into your repositories. Once a secret gets checked into a repository, anybody that has read access to that repository also has access to that secret. And also, if they pull that code down to their local environment, that's now being stored in plain text on their local environment. It's important to keep these things secret. By default, what code scanning is looking for when you just turn it on is authentication tokens. If your applications are using external services like Shopify or Stripe or Azure, GitHub, those sorts of things, probably using authentication tokens to gain access to those services and to gain the privileges that you need to perform the functions that the application is supposed to perform. If anybody gets access to those tokens, then they, of course, get access to those same services and those same functions, those same privileges. Leaked tokens is a way that bad actors have gotten access to S3 buckets full of proprietary information, or PII, data that we're obligated to keep private. It's also a way that bad actors have spun up crypto mining or cloud resources to do things like crypto mining and that sort of thing. And then whoever owns the token is responsible for those charges. So it's definitely important to keep those authentication tokens secure. GitHub has worked with over 100 different partners to create over almost 300 different uniquely identifiable token types like you're seeing here. We worked with these partners to put these uniquely identifiable strings at the front of their tokens so that we could do this kind of searching with a very low false positive rate. We're aiming for a less than 1% false positive rate with these tokens in secret scanning. Low false positives is important because your application security program is going to succeed or fail based on developer adoption. And one of the quickest ways to alienate your developers and make them hate the tool and not trust the tool is to flood them with false positives. So with all of our tools, we strive to keep the false positives low to a reasonable amount so that they're not interfering with the developers doing their work. So the developers don't have to spend time sorting through all of that. So that's why we have these nice, uniquely identifiable token types, token strings. In many cases, we also have the algorithms that we can use to get checksums for the tokens, so that even if something looks like a token, we can run a checksum and see if it is actually a token or not. And then finally, we offer the ability to validity check a token that's been found within your repositories. You can see the ones that are checked here are the ones that we can do that check for. We are able to validity check about 70% of the tokens that we find on a day-to-day basis. And that's not 70% of the different types. That number's a little lower. But of the tokens that we find, typically we are able to validate whether about 70% of them are actually still active tokens. So that's default secret scanning. We also give you the ability to search for these non-provider patterns, we call them. These are also well-structured tokens, well-structured tokens that we can look for with a low false positive rate using regular expressions. But like Adam mentioned, looking for passwords and things like that with regular expressions within code, you're basically looking for unstructured data in lightly structured data. And that is very difficult to do with regular expressions. So we've started using the power of Copilot, the power of large language models, to really do a better job looking for unstructured secrets within your repositories. I'll show you some examples of both types here shortly. In addition to looking for these things in your repositories, and when we look for these, we're not just looking in the code in your repositories, we're also looking in issues, issue comments, issue titles, wikis, all these other text sorts of fields that you see in GitHub. So we're not just looking in the code. We are also searching all branches, the history, and things like that. Now, once a token gets into your code, whether it's a password or one of these generic tokens or one of our provider tokens, partner tokens, once it gets into your repository, that secret is burned. You can't just erase it. Even if you were to erase it completely from the history, you don't know who's pulled that code down and now has that secret residing on their local environment. So it's not sufficient to just eradicate the token from GitHub. Once it makes it into the repository, that needs to be rotated and revoked in order to secure that secret. Now, rotating and revoking secrets can be a time-consuming and kind of a pain in the rear. So another feature that we offer is called push protection. And what push protection allows us to do is block a secret from ever making it into your repositories by scanning it at the point of push before it is actually put in the repository. So here I'm going to go ahead and show you some tokens, or some findings rather. So if we have a look, say, at this Google API key, we can see we've identified a Google API key. It's a publicly leaked secret. It's been leaked in a public repository. I have the token here. We can see that it's been verified. So this is actually, the secret is active. We see the remediation steps. They're always going to be pretty much the same. We need to rotate the secret if it's being used so that we don't break any workflows. We need to revoke the secret so that it can no longer be used to gain the privileges that it entails. Check our logs for breaches and close the alert as revoked. We also see in the alert where the token was identified, and also the commit that introduced it in case we need to go back and educate somebody that, hey, this is a bad practice. We don't want to allow this. So this is what your secret alert looks like and the information that we provide. Now let's look at how push protection works. Let me grab a token. I'm going to demonstrate this here in the GitHub user interface. So I'm just going to edit a file here in the GitHub UI and add a token to it so we can see how push protection works. It'll look a little different here on the GitHub user interface than it would if you were to push in your terminal from your IDE. Pushing from the terminal, you're not going to be able to get a pop-up. Instead, you're going to get a one-time use URL where you can go and see the same information that we're going to see here in the pop-up. So when I paste this secret here into this token here into the file and I go to commit my changes, oh, it tells me, hey, secret scanning found a GitHub personal access token on line 5. It explains to me why this is a bad idea. And then if you have privileges, which I do because I am an owner for this organization, it gives me some options here. If I was not an owner, if I was a typical developer that did not have permissions to bypass push protection, I would get the option to select one of these and request bypass from somebody who did have permission. So if I select it's used in tests or it's a false positive, it's going to create an alert, but that alert will be created in a closed state. If I select I'll fix it later, it's going to create the alert in an open state so that we can track and make sure that I do actually go back and fix it later. So once I select one of these, I would be able to select allow secret, and it's going to go ahead and push that secret into the repository, overriding that push protection. But again, that's only allowed for those who have permission to do so. So that is push protection. Now let's have a look at a finding that is that has been identified by AI. So here we're looking at some various passwords that have been identified using the power of large language models. If I click into one of these, I can see we were asking for feedback. That's available there. And that's because we are still, this is still a relatively new feature. This feature is in public beta, and we're still working to improve it. We've got the false positive rate much lower than it was initially. We initially started trying to do this with older versions of ChatGPT. We've since started doing various things, introducing different algorithms, using multiple type instances of ChatGPT to try to get those false positive numbers down. We got them a lot closer to where we want them, but we're still working on getting them to where they need to be in line with the rest of our tools. But we can see here that, again, this has identified something. Again, if you're trying to find these sorts of things with regular expressions, you have to have a million regular expressions because of all the different things that they can be. And then you also end up with a ton of false positives. So using the power of Copilot, the power of large language models, we are able to get this into a much better state. One of my largest customers has over 80,000 repositories and over 30,000 developers. They've enabled this on all of those repositories, and they've been very pleased with the results. And they're trying to make solid progress towards reducing that backlog of secrets. So that is secret scanning and the power of Copilot to identify secrets within your code. I'm going to talk a little bit about, custom patterns. I forgot to mention custom patterns. In addition to those features that I talked about, we also give you the ability to create custom patterns for things. If there are particular things that you want to look for in your repositories that we aren't looking for by default, then we give you the ability to create custom patterns. And those custom patterns can have multiple fields, making it a little bit easier for you to generate the regular expressions that will find these secrets without having a ton of false positives. So we would give it a name. we would looking for the secret, which typically is going to be like a password or something, and that can be anything, right? The key is going to be looking for something before that secret, like password equals or database equals or user equals or something like that. And then something at the end of that, like the end of line or the close quote for a string, that sort of thing. We maintain a repository of regular expressions that have been useful for us and for customers. And if we click into that, we can see some samples here. So for instance, if we wanted to find, say, database connection strings, I showed you that we have the three different fields. We have the pattern format for what we're looking for. That's in this case, a secret, a password. So it can be just about anything, which this regular expression here will find. And as I mentioned, for our start pattern, we're going to want something like database equals, user equals, source equals, that sort of thing. And for our end pattern, we'll want the end of a line or the end of a string. In order to help you reduce those false positives, we also give you the ability to just have additional, hey, it shouldn't match this, or it shouldn't match, or should match that. So here are those here. So for a custom pattern, I would basically take these and I would copy and paste them into this new custom pattern. And that would give me the ability to find those sorts of database connection strings. And we also have the ability, using AI, using Copilot, the ability to generate custom patterns. So here will give us a natural language description of what we're looking for. And in this case, I want it to help me find credit card numbers that might have potentially been checked into my repository. I'm going to give it some samples. And then I'm going to ask it to generate some suggestions. So it's giving me a couple of options here. And in this case, I can, it tells me why it's generated the custom pattern in the way that it has. And if I click use result, it's going to go ahead and fill those in for me. Of course, I do need to give it a name. So it's gone ahead and entered that for me. And it's identified, well, it's identified one of my tests. Let's try that again. Let's see how it works when we use the other one. More success, but not quite complete success. So it is important to go ahead and validate these regular expressions, but it will help you spend less time going through Stack Overflow or other documentation as you're working to create these regular expressions. It's also important to have good test data. Once you've done your initial testing, we can save and do a dry run. And what that's going to do is it's going to run the scan over the entire scope that I was planning to enable this for. Your custom patterns can be enabled at the enterprise level, the organization level, or at the repository level. That way you can use them where they're relevant and not use them where they might only be producing noise. Once I've satisfied with this and I do my save and dry run, it'll run that across the entire scope for which I'm about to enable it. And it'll let me know what the findings were without publishing them. That way, if I do have a ton of false positives, I can go back and refine it before I actually publish the pattern and start sending results to developers. Once I'm satisfied with it, then that's what I would do. I would publish it and send the results to the developers. So that's secret scanning. That's the end of secret scanning. I expect a lot of you are familiar with Dependabot. Dependabot is available on all repositories on GitHub. I don't have any AI stuff to tell you about with regard to Dependabot, but stay tuned. There might be something coming in the coming days. Dependabot is our software composition analysis solution. What Dependabot is going to do is identify the open source dependencies that are in use within your applications and let you know if any of them have known vulnerabilities. And that's what we're looking at here, is known vulnerabilities in Dependabot findings across our organization. Dependabot also has the ability to create pull requests for you so that when a vulnerable dependency is identified in one of your applications, Dependabot can actually create a pull request updating that dependency in your application, making it, saving a step for your developers in remediating those problems. Here we are looking at Dependabot findings across the entire Octodemo organization. This is, again, our demo organization with about 2,600 active repositories, most of them having intentionally vulnerable applications in them that we're using for demonstration purposes or testing and things like that. We don't fix a lot in this organization. One of the cool things about having these dependabot findings across the organization and being able to search them across the organization is when something like log4shell breaks, you're able to come here and actually see, hey, how are we doing with our remediation efforts? Log4shell broke, say, 2 weeks ago, or some other new vulnerability broke 2 weeks ago, and we need to see, how are we doing in our remediation efforts? How many repositories do we have left that we need to do that for? So let's see if I can. And now I can see that we have still 72 instances of vulnerable versions of log4j, vulnerable to log4shell specifically, because I'm searched for this particular CVE. So I can see that we have 72 instances of those still in place, and I can see the different repositories where that is the case. I can also, if I want to search more broadly, I could just search for all vulnerable instances of log4j, where it's any CVE, not just the log4shell CVE, and we'll see we have more of those. So this is a great place to be able to come and see, hey, how are we doing, like I said, with our remediation efforts on this critical vulnerability that we're trying to fix across the organization. So let's have a quick look at security overview. Security overview is where we come to see how we are doing across the organization with regard to application security. As I mentioned, we're looking at our Octodemo organization with over 2,600 active repositories. And here I can see that 42% of these repositories have dependabot findings. I can see the distribution of those findings from critical, high, moderate, and low across the different repositories. I can see that 36% of our repositories have code scanning findings and 44% have secret scanning findings. I can slice and dice this if I want to see how my buddy Matthew's team is doing. With regard to application security for the 10 repositories that they're responsible for. I can filter for his team, and I can go straight into the findings or to the repositories for any of these. I can also search by keyword. So if I wanted to just find the 2 repositories in this organization that have my name in the handle, I can do that way. So lots of ways to slice and dice this. I, as the organization owner, see all of the repositories in this organization. If I were a developer who had a smaller set of permissions, could only see some of these repositories in the organization, I would see all of these findings, all of these percentages, just for the repositories that I am able to see. I can export this to a CSV. If I want to see, again, want to have a report for how Matthew's team is doing, I can do that. We also have the coverage panel here, where I can look and see how we're doing with regard to adoption across the different tools. I can see that 82% of the repositories in the organization have dependabot turned on, 57% are being protected by code scanning, and 96% are being protected by secret scanning. And I can slice and dice these the same way. Again, if I want to see how Matthew's team is doing with regard to adoption, or how my repositories are doing with regard to adoption, I can do that as well. We have enablement trends where we can see what percentage of the repositories are using each one over time. As you can see, ours are pretty static. But I know in an organization, when you're rolling these things out, it's very useful to be able to see how that is going over time. We can also see things like how many autofix suggestions are we seeing, and which ones are being fixed via autofix and that sort of thing. And I can see the various campaigns that are in place across this organization. As I showed earlier, if I go to the code scanning findings, I can see all of the code scanning findings across the organization. I can filter that. I can look at the different tools that have been integrated, or whose findings have been integrated here into GitHub. And again, lots of ways to slice and dice these things. I can create a new campaign. I would do that by filtering to the kinds of alerts that I want to include in the campaign, and then clicking that Create Campaign button. So that is the general overview of GitHub Advanced Security with Copilot, or with AI powered. Shoot, what are we calling it? GitHub Advanced Security with the power of Copilot. So if there are any questions, I see there's some. If there are any questions, you can feel free to put those in the comments, and we will come back with those. Or Adam, if you had anything that you wanted to add.
Nothing to add. Fantastic job, Charlie.
Thank you. So we'll give folks a few minutes if they want to add any questions into the comments, and if not, we will bid you adieu.
Thanks, Charlie. And while we're waiting, I'm just going to throw this slide up here for us. We are always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. The link for that is on the screen, and I'll also drop it in the chat. Today's event code is 23924, and we'll hang out here for you. If you have any questions, please feel free to drop them in the chat. We'll see you at the next one.